Hello everyone, welcome back to my YouTube channel. Myself Kirtana HR, currently pursuing in second year BE in the Department of Computer Science and Engineering at Sri Venkateswara College of Engineering, Bengaluru. Today's subject, data structure and algorithms, and the subject code BCS 304. And today's presentation is on parallel packed memory array to store dynamic graphs. Now let's see the agenda. The first one is introduction, and then challenges of dynamic graphs, background, parallelization strategies, performance results, and the conclusion. A parallel packed memory array to store dynamic graphs. This paper is written by Brian Wheatman. Now let us see the introduction. This presentation introduces a novel data structure called the parallel packed memory array that enables efficient storage and management of dynamic graphs. This parallel packed memory array builds upon the packed memory array data structure, adding parallelization strategies to support fast concurrent updates and catch efficient range queries, key requirements for real-world applications like social networks and networking routing. Let us see challenges of dynamic graphs. The first one is fast updates. Dynamic graphs in applications like social networks and social routing requires efficient ways to handle frequent challenges to the graph structure, such as adding or removing nodes and edges. The second one, efficient range queries. Performing useful graph analysis algorithms like breadth first search and betweenness centrality requires the ability to efficiently query and traverse subsets of the graph. The third one, balancing performance. Existing data structure like static compressed pair raw and hash tables struggle to provide both fast updates and efficient range queries, particularly for dynamic scenarios. Background, that is, packed memory arrays. First one, definition. A packed memory array is a data structure that stores elements in an ordered fashion with graphs between elements to enable efficient updates. The next is advantages. A packed memory array support fast range queries with O of log n plus k, work for k elements, and amortized O of log square n update cost. This makes them suitable for dynamic scenarios. Then challenges. However, in the worst case, updating a packed primary array requires restricting the entire data structure, which can be computationally expensive. The parallel packed compressed sparse raw. The concept. PPCSR extends the PMA data structure to efficiently store and manage dynamic graphs. It leverages parallelization strategies to enable fast, concurrent updates and case-efficient range queries. Features. PPCSR supports concurrent readers and writers with locks to prevent data races. It also includes optimizations like batch processing to further improve performance. The performance. PPCSR has been shown to achieve up to 80 million updates per second, making it a highly efficient solution for managing dynamic graphs. Now let's see parallelization strategies. Intra-operation parallelism. PPCSR uses a divide and conquer approach to parallelize individual operations such as updates or queries across multiple threads. Intra-operation parallelism. The data structure also supports multiple threads performing updates or queries concurrently, further improving overall performance. Synchronization. PPCSR utilizes locks and other synchronization mechanism to ensure data consistency and prevent race conditions during parallel operations. Experimental evaluation. The first one is comparison systems. PPCSR was evaluated against other dynamic graph processing systems including Aspen, Liger, and Liger Plus. Algorithms tested. The team measured the performance of PPCSR on common graph analysis algorithms such as breadth first search, betweenness centrality, PageRank, and connected components. Datasets. The experiments were conducted on a range of real-world and systematic dynamic graph datasets, including LJ, ER, ORKUT, and RMAT. Performance results. Speed. The results show that PPCSR outperforms the Aspen system in the most cases and is competitive with the performance of static systems like Ligra and Ligra Plus despite PPSCR's support for dynamic updates. The next is memory usage. While PPSCR uses more memory than the highly compressed systems, it is able to maintain fast update performance, making it a suitable choice for applications that require both efficient updates and range queries. Insert throughput. First one, small batches. For small batches of updates, that is up to 1 million, PPSCR demonstrated a 2 to 5x faster insert throughput compared to the Aspen system. The second one, large batches. However, for larger batches of updates, that is 10 plus million, PPCSR's scalability was slightly less than Aspen, though it still maintained a competitive performance level. The last is dataset variations. The insert throughput of PPCSR was evaluated across a variety of dynamic graph datasets, including LJ, ER, ORKUT, and RMAT. Now let's see the conclusion. The parallel packed compressed sparse raw data structure presented in this work addresses the key challenges of managing dynamic graphs by leveraging parallelization strategies and building upon the packed memory array data structure. PPSCR achieves high performance updates and efficient range queries, crucial capabilities for real-world applications like social networks and network routing. The experimental results demonstrate the advantages of PPCSR over existing dynamic graph processing systems, making it a valuable tool for computer science researchers and practitioners for working with large-scale evolving graph data. We hope this presentation has provided you with a true understanding of the parallel packed compressed sparse raw data structure and its potential applications in managing dynamic graph data. For more information or to discuss potential collaborations, please feel free to reach out to the authors. Thank you for your time and attention. Now let's see literature review. Parallel packed memory array for storing dynamic graph is an emerging research area that combines graph theory, memory architecture, and parallel computing. This literature review explores the fundamental concepts, challenges, and advances in using PPMA for dynamic graph storage. It covers topics such as graph storage models, dynamic graph representation, memory array designs, and parallel processing techniques. The first one is graph storage modules. The second one, graph storage, is fundamental to many computing applications from social networks to bioinformatics. A graph consists of nodes, that is vertex and edges, and its storage model determines how efficiently the graph's data can be accessed, modified, and traversed. The third one, dynamic graphs and their challenges. And the fourth one, a dynamic graph is one where the structure, that is, example, the vertex and edges, changes over time due to insertion, deletions, or updates. This presents challenges that are not present in static graphs. Thank you everyone for watching my video.